Ladies and gentlemen, welcome to the 2013 Shaw Prize Lecture at HKUST. I'm Bing Jing, Professor of Mathematics and Acting Director of the Center for Statistical Science. Indeed, it's a great honor to have the Shaw Lecture to be delivered by one of the greatest minds of our time, the very handsome, the one and only, Professor David Donohoe. Now, the Shaw Prize is an international award established under the auspices of Sir Run Shaw to honor individuals regardless of race, gender, nationality, and religious belief who have made significant breakthroughs in academic and scientific research or applications, and whose work has made positive and profound impact on mankind. And it consists of 3 annual prizes: astronomy, life science and medicine, and mathematical sciences. And of course, this year's prize goes to Professor Donohoe. So first, may I invite our president, Tony Chen, to give a welcome speech.
Good afternoon and welcome everyone. This is quite a crowd. I'm sure you will not be disappointed. I would like to extend my warmest welcome to all of you today for coming to this Shaw Prize lecture in the mathematical sciences to be given by Professor David Donohoe, who is the Ann T. and Robert M. Bass Professor of the Humanities and Sciences at Stanford University. He's also the Professor of Statistics at the same university. Now, Professor Donohoe is the winner of the 2013 Shaw Prize in the Mathematical Sciences. He won the prize for his profound contribution to modern mathematical statistics, in particular for the development of optimal algorithms for statistical estimation in the presence of noise, and efficient techniques for sparse representation and recovery in large data sets. The Shaw Prize is one of the most prestigious prizes that can be bestowed to a researcher. In particular, you probably know there's no Nobel Prize in mathematical sciences. Okay. Winning the Shaw Prize is a testimony of the immense achievement of Professor Donohoe. As a member of the selection committee for the prize, I am so happy to be involved in the process of awarding the prize to Professor Donohoe, whose status can be best summarized by a leading expert we consulted. This expert described Professor Donohoe as the most influential theoretical statistician of all time. He did not comment on him being handsome. Okay? That was not a factor in the selection. Professor Donohoe will speak on the topic compressed sensing, past, present, and future. Professor Donohoe is instrumental in the development of this beautiful algorithm. In fact, I would say a whole framework that compresses while sensing. For those of you who are not familiar with this, every one of you has a digital camera. And you all know when the more pixel you buy, the more you pay for. But it compresses, right? The file you have is compressed. So imagine something that when you take the picture, it already compressed. So you don't need to buy 20 megapixels or whatever it is. So you hear about that. That's only one of many, many possible applications of this view. Anyway, this compressive sensing would enable the construction of signals and images from much fewer measurements than what we thought necessary traditionally. This technique has a great impact to our daily life, with application ranging from medical imaging to oil exploration to astronomy. One example is actually MRI, magnetic resonance imaging, which compressed sensing has greatly reduced the time it needs for the scanning process. Another example is it's used in a mobile phone camera sensor to reduce battery drain. In fact, this technique opens up a wide range of possibilities, and Professor Donohoe will give us his insights on the future trend in this lecture. Before I leave the floor to our distinguished speaker, I would like to thank the Shaw Prize and Sir Run Shaw for bringing the Shaw Prize lecture to our university every year. Not every year is in life science, in the mathematical sciences, we rotate. These lectures provide golden opportunities for HKUST, students and faculty, and in fact the extended community, to meet great minds and be enlightened firsthand. This is especially the case for our young audience. I always encourage our students to take advantage of the rich offerings of great lectures at HKUST. And I'm really pleased to see many of our students, as well as students from sister institutions, actually students and faculty from sister institutions, and also a student from secondary schools among the audience. I'm sure all of you will come away today filled with inspirations and aspirations for higher goals. I'm also delighted to see colleagues from various disciplines, statistics, information systems, electrical engineering, etc., here today. The visit of Professor Donohoe and other great scientists will certainly provide excellent occasion for our colleagues to interact with the world's brightest minds. Professor Donohoe came to HKUST last week as a guest of our Institute for Advanced Studies, and we look forward to more collaboration with him in the future. Last thing I want to say is that it just happened that Professor Donohoe is a longtime professional friend of mine, and we have met in many conferences and so on. So I'm somewhat familiar with his area of research. So in fact, I know a few of his distinguished students as well. So I know firsthand the impact that Professor Donohoe's work has had and will have in the future. I'm also very glad that he and his wife, Mickey, has accepted our invitation to come for a whole week before the ceremony. And I hope you like Hong Kong and HKUST enough that you'll come back and return to visit HKUST and Hong Kong in the future. I'm sure you'll be very welcome. You see the reception here for you today. So ladies and gentlemen, it's my honor to present Professor David Donohoe, one of the greatest applied mathematicians in our generation. Please give him a big hand.
Thank you, Professor Chen. Before we start, I would like to present a souvenir as a token of our appreciation. Yeah. So the souvenir is a miniature replica of the carved mural found on the Sandao podium on campus. It depicts 39 ancient Chinese achievements in science and technology, many of which are actually related to mathematics. So please. Okay, now we can have the lecture. Okay, start. Thank you.
So I've been told there are some secondary school students here. Can they raise their hands just to get an idea? Okay, good. So I've salted my talk with some material that it will inspire you, even if later on there are things that feel that are beyond you. You can see the continuity with what we're going to start with. Okay, so imagine that we have three thieves who don't trust each other. They have to share a secret. The secret is the location of a treasure. The treasure is in three-dimensional space, and the location is a set of three numbers that specify where the treasure is. The thieves are afraid that there could be a conspiracy against any one of them, so that, for example, you could have two of the thieves try to take the treasure and not give the third thief what he's due. So it's absolutely essential to have a way that all three have to participate in the recovery of the treasure. All three have a piece of information that they themselves hold that the other two can't live without. How can we solve this problem? So what we want to do is with these rules is give each thief a partial secret, and when they're all combined in a special ceremony, then the location is revealed, and then all three of the thieves march to that place in three-dimensional space, and they share the treasure. Everybody got the picture? So here's a solution to that. We give each thief a hyperplane. When the three hyperplanes, and of course each thief keeps his hyperplane secret until the key moment, and then when those three are unveiled, notice that three hyperplanes in space generically intersect in a single point. That's the point where the treasure would be. So it's clear that for any point in three-dimensional space, we could construct such a system of hyperplanes, and it's clear that we could make this system work as a technique for secret sharing. Everyone agree? Are there any questions about this? Okay, what makes this work in the end is that the numbers x1, x2, and x3 that give the location of the secret in space are being specified through a system of equations. Namely, when each thief has a hyperplane, what that really means is that there are four numbers that that thief has that the other ones do not. So for example, we write out the equation of a hyperplane as y1 equals a11x1 plus a12x2 and so on. Could I have a laser pointer, perhaps? Do we have one? Apparently not. Okay. So the first equation is actually the equation of the first hyperplane. The second equation is the equation of the second hyperplane. The third equation is the third. Solving those three simultaneously is the same thing as saying that we intersect the three hyperplanes. So the visual proof that we had on the preceding slide is equivalent to the statement that there's a unique solution to this system of equations. And even if you're a secondary student, I think by now you will have heard about solving systems of equations like this. And you will have been told that equations like this are solvable at least under certain conditions. We gave a visual proof, and you can do the analysis behind the solution of these equations. They're equivalent. And what we're exploring here is the following notion, which could be called the fundamental theorem of linear algebra, although maybe we don't because it might sound scary for school students. And it would say, if we want to determine a point in three-dimensional space, we need at least three equations. And we can do it with exactly three equations if we choose just the right kind of equations, namely ones that exhibit a property called linear independence. Now, there's a generalization of that to higher dimensions, which is going to be very useful for the rest of the talk. Imagine now that instead of something that's taking place in three-dimensional space, we permit ourselves the abstraction of jumping up to a large dimensional space, capital N-dimensional space. The object of interest is still called x, but instead of 3 coordinates, it's got n coordinates. And instead of 3 equations, we're going to have little n equations. Little n is not necessarily equal to capital N because I want to make a didactic point. Namely, we can have a different number of equations than we have variables that we're trying to solve for. That's for the purpose of discussing what might happen if we try to do that. So the generalization of this fundamental theorem of linear algebra to higher dimensions would be that if we have to determine an object that has capital N coordinates in a capital N dimensional space, well, of course, we're going to need at least little n that's at least as big as capital N. Despite the typographical suggestion, we're not allowed to have little n be smaller than that. That's the one thing that the fundamental theorem of linear algebra would be utterly sure about. Thank you. So let's just make a little emblem, kind of a logo for the talk. In this logo, our system of equations is going to be indicated by this multicolored array. And what I mean here is that there are different numbers. So it's a rectangular array where each one of those is standing for one of the coefficients in the system of equations that we were talking about. And the different colors are just to suggest that you could have a variety of different numbers present in the array and so on. And then those values of y that we saw populating the equation on the previous slide are indicated here, again with various colors. And then the unknowns x are all white here in this little emblem because we haven't solved it yet. We don't know what values x would go in there. And this is an emblem for solving a system of equations. Another thing that we'll use in the talk is matrix vector multiplication, where we have y equals ax. A is the array here that we've been talking about. Y and x are vectors. Y of size little n and x of size capital N. Now, in this form, what I want you to notice is that this matrix A is short but fat. Okay? The fundamental theorem of linear algebra says it's no good to be short and fat. You either have to be square or you have to be tall and skinny. Those are the only things that the fundamental theorem of linear algebra likes. And you can draw your own conclusions about whether that means anything in the rest of the world. But what we've seen is that there's a basic phenomenon in mathematics that we have and that everybody knows. If we work in science in general, let's say as a physicist or a chemist or something like that, there's a method that's called parameter counting. If I want to know how many pieces of information I need to solve a certain problem, I can just count how many things are needed to determine the answer. The fundamental theorem of linear algebra says that if the underlying x that you have has capital N entries, then the underlying y that you're going to have to use to determine it has to have at least capital N entries. And in particular, it's no good to do what's being done in this picture. It would be great if we could do it because it would say that with very little information, we could determine this thing, but fundamental theorem of linear algebra says no. Any questions about this? Okay, so now let's think about something that's more mundane. Say you have a small child and they have to sit in an MRI scanner and if they're really a small child, they talk to their parents and ask a lot of questions, and then you have to keep going and going and going. So the first question is, why do I have to sit still in that contraption for name whatever your length of time is? And, the correct answer is, well, we have to make little n equals 10 to the 6th measurements. And then, then the thing that comes, why do we have to make little n equals 10 to the 6th? Well, because we have capital N equals 10 to the 6 pixels. Well, what do you mean by that? Of course, if we've got an image and we think about what's really going on, we blow it up, and we have an array here of pixels. Each one of them, there's some numerical values that's indicating the intensity of light that goes in there. Actually, if it's color, it might be 3 numerical values for the red, green, and blue, but we'll just ignore the colorization aspect. And so we're by now familiar with the idea that your display involves lots of pixels, each one of which is numerical. And so an image that you have is actually an array of numbers. If it's a 1,000 by 1,000 image, which would be common in many cameras now, in fact, it would be rather small for some of them, well, then you actually do have 1,000,000 pixels. Okay, is that clear? So if we go back to the question, What's the real reason that we have to sit in the scanner? It's because of the fundamental theorem of linear algebra. So here's one of those things where math is playing traffic cop. It's telling you, you have to stop. You can't do this, et cetera, because it's telling you that you need a certain number of measurements if you have a certain number of pixels. Well, in today's talk, we're going to relax this. And we're going to show that those forbidden things that are short and fat actually can be accommodated in some sense. And we're going to show that in a certain sense, you can violate the fundamental theorem of linear algebra, provided you know what you're doing and you use a sophisticated approach. So let me tell you a little bit more about this. It's sort of an evolving flash crowd. If you go in either ISI Web of Knowledge or PubMed and just start looking at hits on the term compressed sensing, you see that somewhere soon after 2004, this starts to take off at a significant upward slope. And even in medicine, which is a subfield of all of the things covered by ISI Web of Knowledge, you see that also starts to take off with about a 2-year delay. Of course, you could also look at a variety of different terms. Sometimes it could be called compressed sensing. Sometimes it could be called compressive sampling. There's a series of highly cited papers, and you can see some of them, at least in the Google citation sense, get into the thousands of citations. This is an interesting development. It's a sudden flash crowd in publication. It's interesting for a variety of reasons. One is there are all sorts of fields contributing to it, and there are all sorts of angles that people have found. So that, for example, in mathematics, you see people coming from many different angles that were previously thought of as distinct, unrelated fields, and suddenly they're all publishing in this area. In fact, if you look across the applied mathematical sciences, you can find people publishing from many different angles, all again making contributions here. So you have statistical physicists, you have people who are interested in quantum information theory, you have information theorists, you have people who classically just did design of experiments, and you had people who developed high-performance mathematical software, all contributing under this same search term. And then finally, there are applications out in the world that are being developed over a variety of fields. And as President Chan mentioned, magnetic resonance imaging, which I'll give examples from, seems to be making the quickest progress. But we also see, for example, high-resolution radar. We see compressed genotyping and screening for rare diseases, and there's using next-generation sequencing. So there's a variety of different things that this can do. And it's all from the promise of violating the fundamental theorem of linear algebra, again, given that you know what you're doing. Okay, so given that we have this flash crowd, what I'd like to cover in this talk, and I don't have it specifically structured to answer every one of the questions that is raised here with a subsection. If I forget something, please hold me to it at the end and I'll try to answer for you. So where have we gotten to now? How did we get here? What set of steps got us there? Why did everything start taking off in 2004? What happened before that? Because there's a prehistory that I'll talk about. And where are we headed? What's going to happen next? These are some things that I think are appropriate to discuss. So in order to discuss where we are now, let's first just take some practical examples of ongoing research in magnetic resonance imaging. I gave a plenary talk at the ISMRM meeting in Melbourne, Australia, 2012. There's about 5,000 physicists and MDs who come to that, and I had an audience, about 2,500 of them in my talk, and I learned what was going on. The biggest single topic in that conference, which is the biggest conference in the field, was compressed sensing and MRI. So it's a good place to start. It's something where, you know, people think there's an impact, and there are demonstrated experiments that are causing the excitement. Here's an example of what we're talking about. Radiology is the flagship journal for advances in standard of care by research in MRI. So if you can get your paper in there, it'll be held to the highest standards and be considered very influential. So there's a paper there by scientists at Lucille Packard Children's Hospital at Stanford and UCSF, improved pediatric MRI via compressed sensing. The MD on the study was Shreya Vasanawala at Lucille Packard, and Michael Lustig was the PhD on the project. The project went like this. Radiologists were blindly scoring images that they were presented. They didn't know what was the method of construction, so they didn't know how the data were gathered, and they didn't know what processing had been done. They had to take those and judge them as being either diagnostic quality or non-diagnostic. And the underlying intervention that was being done is that in some cases, the images were based on a sped-up acquisition of 6.8x, followed by some very special processing. And in the other cases, things that were done were just the current state of the art, which is just based on linear algebra. The radiologist in this case agreed that the 6.8x speed up was producing images that were diagnostic quality and had high confidence. So this is not mathematicians talking about it. This is the actual end user doctor saying, yes, these are images that are good quality for me. So if you tried to do the same speed up using traditional processing techniques, they judged those methods not acceptable. So I've got some external demos, and these are things that were produced for me by Mickey Lustig, who's now he got his PhD at Stanford, but he is junior faculty at UC Berkeley. Let's see, how do I get started here? Okay, so the problem with children in MRI is that they won't sit still. In the initial study that was in radiology, the acquisition speedup was from 8 minutes to 70 seconds. What you would like is the child to sit still so you can get good quality cross-sections of the body, but with a typical child, when they become restless, this is what you get, and that's very useless. To get one of these things going on in an actual clinic in daily use, which is what's happening at Lucille Packard at Stanford, there's a lot of things that you have to do. You have to have special scanner hardware to implement your protocol. You have to have a lot of computing equipment to run your algorithms. You have to have staff to get all this stuff going, et cetera, et cetera. Here's an example of a result. This is a 16-second acquisition, so that things have now been sped up to the point where, at least when you're talking about something that's based on contrast, the child here has something intravenous, which is allowing it to, in some sense, illuminate the body. You can, in just seconds, acquire an image. Here's an example with all the appropriate labeling on it, showing the difference between what would happen with state-of-the-art but fast acquisition, which would be this grainy picture on the left, in which it's very difficult to see things. And on the right would be the technique that I'll speak about later in the talk. You can see it's like night and day. For the same amount of acquisition time, this is useful, this is not. So you really do need to understand what you're doing and use approaches of this kind. And if we blow this up and look at very specific structures that someone would be interested in seeing, there's just not even an evidence if you use traditional linear reconstruction, whereas they're clear and the radiologists have scored them as having diagnostic quality. Now I have to go to a different example. There are more ambitious things that are being done, even beyond trying to get factors of 10 and more speedups. This is an example of, instead of making a static image, like a 2D image, this is to actually get something that is in some sense four-dimensional, because there's going to be an image, there's going to be time, which gives a third dimension, and there's going to be metabolite amount, so that you can actually know that various processes are going on pixel by pixel. In this case, the metabolites that you're interested in are things like lactate and pyruvate, and please, I'm no expert on any of this. I just want to illustrate the kinds of things that are being done. This is in a prostate cancer model, and the basic point is that there's a tumor that can be tracked. It's possible to actually see dynamics that are associated with metabolite levels. It's possible to see them as you go slice by slice through the body. It's also possible to see things evolving in time. The ultimate ambition is to be able to go to extremely detailed information, which is in some sense like a five-dimensional experiment. Let's say 3 dimensions of space, a dimension of time, and a dimension of metabolite intensity. And as you add dimensions, N, capital N, is growing exponentially in that. And so research of this kind is really pushing where we want to go by using the techniques that we're talking about. I don't claim that it's all there yet in these things. These are the kinds of talks that you see being given at ISMRM, where people are showing that they're delivering the beginnings of applications that no one ever thought they would see, and now they're able to make progress on that. Are there any questions? Okay, so Michael Lustig is the fellow who was doing those applications, and essentially what was his thesis was a paper in magnetic resonance in medicine, and it has about 1,400 citations to date. That's really good for a thesis. A lot of people never get that in their life, and so obviously this young man is having some impact. Okay, so the reason that so many citations have come down is that we've gotten to a place where we can describe something that a researcher can go try out in an applied field, and it's a very crisp, compact thing that you have to understand, and then you can go do. And we can summarize it with an emblem like this. First of all, you can think of the underlying object X that you're interested in as one of these vectors. You can think of compressed sensing as taking one of those matrices that's, again, short and fat, and delivering relatively few measurements. That is, when you hit this against that matrix, what comes out is relatively few numbers, not nearly as many as you thought of originally. But then you take those and you push them through a special algorithm, and what comes out of it is a reconstruction of the tall vector. So we can understand the first part was associated with the forbidden zone of the fundamental theorem of linear algebra, and the second part is some new algorithmic trick. But you've got to be asking yourself, the fundamental theorem of linear algebra is a theorem. So how can we be doing this? The key thing here is I want you to notice that now there's white cells in here, and then there's some colored ones. That's to remind you that there's some assumption that's being made that we're adding so that we can get out of the zone of being forbidden by mathematics. The assumption that we're doing that enables mathematics to help us is that although we don't know which cells necessarily are essentially zero, there's a lot of zeros in there. And that's called a sparse vector. So we can't say in advance where they are, but we're confident that there's sparsity present in that vector. Okay. In that particular case, the claim is that you can go through these two steps and get back that sparse vector. And so even though we violated the naive theorem that we spoke about in the beginning, by using implicitly the fact that there's a lot of zeros here, this whole thing just works, and you get back the image that you want. So in order to explain the heuristic behind that, I'll again switch programs here quickly. Now, a regular image definitely is not something that's filled with zeros. When I look out at this audience, I see a very complicated image. There are all sorts of colors, there's all sorts of light and dark, and so on and so forth. It's anything but a bunch of zeros. The key thing is that I can change the basis of my high-dimensional space that's representing the image to a new basis, and in that basis, what will happen is the image sparsifies. So actually, what you see over here on the right is what's called the wavelet transform of the image on the left, actually a grayscale version of the image on the left. It's actually a coordinate representation of the image on the left in a different basis than the standard Euclidean basis. It's a basis that's multi-scale and has objects at all different locations and scales in a certain organized way. The key thing about the coefficients in this basis is that you see a lot of black, and that corresponds to coefficients that are practically zero. That means that the wavelet transform is sparse. Now, this is an understood concept since about 20 years. Wavelets in digital signal and image processing came in, let's say, 20 years ago, and by the mid-90s, it was really well understood that these have intrinsic advantages in sparsifying image content where we don't know exactly where the zeros are going to be in advance, but we're sure there's going to be a lot of near zeros. Some of the individuals involved in wavelet research, for example, Ingrid Dobuchy, Stefan Millat, Yves Meyer, all have books that you can consult to learn more about this. And you know, there's wavelet meetings in which people walk around wearing wavelet t-shirts and so on and so forth. It's a fun group if you want to find out more about that. What I wanted to just show you is now if we talk about the kind of medical imagery we were talking about, you can understand that that's sparse. And here's a nice demonstration that Michael Lustig made. In this demonstration, what we're going to do is show you on the left an image based on a partial reconstruction using the wavelet transform domain, where we only keep a certain fraction of the wavelet coefficients, a very small fraction. And then we're going to see how the image changes. So we start out, we have a percent, 2%, 3% of the coefficients, 4%, 5%. Then we'll start over so you can see as we go through the fraction of the coefficients, the image fills in. But actually, even by about 1%, you basically are seeing pretty much everything that you're going to see. And so what that means is that the image seems to have, let's say, 1,000,000 pixels, but maybe it only has really 10,000 numerical things going on in it. It's not nearly as data-rich as it would seem if you go into the sparsity revealing basis provided by the wavelet transform. So you have to know that sparsity is a phenomenon that you can reveal by choosing the correct transform. Okay, so then if you remember the emblem that I showed before, we said that you have to have sparsity is the assumption that we're making, and then you have to have a special algorithm. This particular algorithm is called L1 norm minimization, and I'll now just show you a quick demo of that. Okay, let's imagine that we have a sparse signal indicated by that point, and in this case it consists of 2 zeros and 1 non-zero. It's a very simple thing. Now, if we make one single observation, so we only know one of those equations that the thief had, right? We're thief number 1. Then we know one hyperplane. And the claim is, generically, that's enough to recover this thing when the object is that sparse, provided you use the right algorithm. And what the right algorithm is L1 norm minimization. That is, namely, within the hyperplane that you know must contain the solution, find the point in that hyperplane that has the minimum L1 norm. The L1 norm is the distance from the origin that's measured by the size, how big this ball is that grows out to touch you. So how far it has to be dilated to reach you. And it's also the same as city block distance if you live in a perfect grid. What you see here is that the L1 norm, when it first hits that hyperplane, as you grow it outward, it hits exactly along this axis, which is exactly the thing you would want to do. Now, usually when we teach numerical linear algebra, we teach people to minimize the L2 norm, but that would be wrong in this case and would not give you the right answer. Can everyone can tell? Okay, so there's something special about the L1 norm, and I think at this point, it ought to be possible for people to start to see that this is making some kind of sense. So anyway, here's our emblem: sparsity, undersampling, and then recovery using L1 norm. Now, how did we get there? Well, first of all, there's another fundamental theorem that gives us permission to even think this way. And it says that if we have a generic n by n matrix, and so we have a system like this and we don't know anything about what generated it, we just know the left-hand side and we know the entries in the matrix, it turns out that if you go searching for solutions that you know to be sparse, generically what's going to happen is if there's a sparse solution, that's the only sparse solution. Every other solution is completely dense. So that the sparsity alone is enough to tell you you got it. Like if you can find a sparse solution, there is no problem about non-uniqueness. Of course, there's some conditions there. As mathematicians, we choose very carefully how to do things. But the interpretation is there's an optimization algorithm. If we knew how to do it, it would be great. And that is that we would minimize the number of non-zeros in the thing that we're trying to recover, subject to when you push the object that we're trying to recover through the matrix and regenerate the data, you get the data that we actually observe. The problem with this is that because this kind of function is so inherently about counting, that this is in a class of well-understood combinatorial optimization problems, and this is what's called an NP-hard problem in general. And the only way that you could guarantee to solve this for large n of the kind that we're talking about, n of millions, or if we go to really ambitious experiments in 5 dimensions, it could be billions or trillions. You could never guarantee to do something of that nature. But it turns out that for many matrices, a miracle occurs. Namely, there's a convex optimization problem that we've just spoken about, that minimizing the L1 norm that we just did on that demonstration slide. It's also called basis pursuit. It's computationally feasible because it's a so-called convex optimization problem. The L1 norm, city block distance, having this nice property of convexity means that we have 60 to 70 years of fantastic experience in computational science of how to solve these things. And we know that that can be done in large-scale problems. It turns out that often the solution to P1 and the solution to P0 are identical. And therefore, you just have to solve this one, which is feasible, even though we have theory to say this is infeasible. Under some conditions, they're often the same. We just want to elucidate those conditions. And indeed, this has inspired many, many papers, for example, in IEEE IT, but also in other journals throughout the math sciences, to understand this equivalence between L0 and L1. And various hints at this have been available in the literature in various ways. And maybe the earliest that I could trace, it's not written in the particular language, it doesn't have sparsity, et cetera, but it has an idea, is a Bell Labs researcher and famous fiddler named Tex Logan. He was a backing musician on many important Nashville albums. But his Columbia University PhD thesis in 1965 has a lemma that's highly relevant to this whole subject. Will Symes and Fadil Santosa were doing a follow-up to some experiments that had been done in oil exploration and worked on a particular problem of underdetermined equations, missing all the low-frequency information. And then there's a series of other papers. I've listed here some co-authors of mine, and then building up to, in this last row, some individuals who came in around 2004 and started to add into the mix. So in particular, Manuel Condez and Terry Tao in 2004 wrote some papers that got a lot of attention. And after that, you wouldn't be able to talk about a small list of contributors. So all of these people were a small group, and he was my co-author, as are all of these other people. Up until then, like I wouldn't even be able to know all the people working in this after Terry and Emmanuel went around explaining their results. So what happened in the early work is that it was essentially to take that picture that I just showed you, how L1 works in that very special three-dimensional example, and show that it's a little more general or even a lot more general. So there were arguments based on so-called coherence, and then arguments based on restricted isometry property that did give guarantees that you can recover despite violating the fundamental theorem of linear algebra when you have sparsity, and that it's stable even if there's noise. And the early work was all about, well, what can we show in our bounds about the allowed sparsity, which we'll call the number of non-zeros k. The earliest argument showed that if, that should be a plus sign, excuse me. If k is less than n to the 1/2, so if it's only square root of n non-zeros, then you can do something. And then later arguments almost got up to be proportional to n. This is the sort of thing that Manuel and Terry worked on. I thought, again, to carry along some general math culture here rather than talk about precise inequalities and details, I would, at this point, bring in something that really leads to necessary and sufficient and exact understanding of this problem, and also has a beautiful mathematical pedigree. This has to do with some topics in polytope theory, so I'll just remind you a few basic facts. I need this bag here. Okay, so this says something about the miracle continues, and okay. Okay, so I have a supply of objects here. Okay, this is a cube. Everybody understands that. And it's it's convex in the sense that everything that we think of as the solid cube and the inside can be gotten to by convex combinations in between 2 points on the boundary. The sides don't pucker or anything like that, right? And it's a polytope in the sense that it's polyhedral, namely it's got vertices, edges, and faces, and it's built out of that skeleton in the obvious way. Here's another set of, this is a simplex, and it's got 4 vertices, and you can see that it's got 6 edges. It's got 4 faces of dimension 2 and one face of dimension 3 if you think of the solid object. And here's an octahedron that's slightly distorted because we didn't have quite the right Zoom Tools kit in order to give you that. Zoom Tools is a way of building these models. And you can do much more ambitious things than this. This is just the basics. But you can see this is what the L1 ball looks like in dimension 3. Okay, so these are polytopes. And polytopes of this kind, the 3 that I've just shown you, are called the Platonic solids. There are a number of Platonic solids. The 3 that I've shown you are the only ones that exist in all dimensions 3 and higher. So there are other things you will have seen to do with icosahedra, dodecahedra, and things like that, but they don't count because they're special to 3-dimensional space, and we're interested in high dimensions, and those are the only ones you can do in high dimensions. Okay? Now, we're going to talk about the projection of a polytope from high dimensions down to low dimensions. So what do I mean by that? If I tried to show you a 4-dimensional simplex, I could write out for you equations, I could develop for you an understanding of what's going on. If you tried to visualize it, you could only do that in 3 dimensions by making something that gave you some insight, or maybe 2 dimensions. We're creatures of these low dimensions. So we really do have to develop a feeling of projecting from higher dimensions down if we want to understand higher dimensional space. So here are some examples of projecting higher dimensional objects. There's a projection of a simplex. So in 4 dimensions, a simplex has 1 more vertex than it has in 3. And so you see that there's sort of an outside that looks like the original 3D simplex, and then there's another vertex, except that its image under projection falls in the middle. Do you see that? You got one more point, right? The octahedron similarly has extra vertices as you go up. And in this particular plot, you see a whole bunch of them land in the middle. And if you go to hypercube, you see a whole cube lands in the middle. And if you ever had to try to understand these things, you notice that in any visualization you do, what always seems to happen in visualizing high-dimensional polytopes projected down into lower dimensions is exactly what we see here. Some of the high-dimensional structure lands in the middle. Do you know what I mean by middle? We're talking about convex polytopes. So the natural way to think of that is that it's really the outside that matters. That's the polytope. There really isn't any inside, except for just a solid piece of space. So although we visualize this guy here as, well, something landed in the middle, if we actually took the convex hull of what landed down in 3-dimensional space, that stuff in the middle isn't even there. And so what happens is only part of the high-dimensional structure is actually surviving the dimension lowering process. And you see that in all of these cases. Okay, so that's the intuition. It's the intuition that we all share. You've all seen this in some way. It's sort of part of your culture, even if you never thought about it. that something's getting lost when you go to lower dimensions. Well, but it turns out that that thing of getting lost is exactly at the heart of what we're talking about. Namely, it turns out that in the theory of polytopes, we let C capital N be the capital N dimensional octahedron. That's the standard notation. I don't know why. Projection, we're going to achieve by having a matrix of the kind we've been talking about, and we're going to lower dimensions by taking this polytope C capital N and lowering it down into little n dimensional space. And that's exactly what we did on the previous. You remember the blue thing was the lowering of the octahedron from 4 to 3-dimensional space, right? And what we saw is that, for example, a bunch of stuff that was initially on the boundary in high-dimensional space landed on the inside. Okay? That's really concerning because it turns out that's the one thing we don't want to have happen. And here's a theorem that captures for us very crisply, in a way that you just can't forget it once you know it, everything that's going on. It says that those optimization problems, P1 and P0, have the exact same solution if and only if, like it's a complete characterization. If and only if what? Well, the K minus 1 face of the octahedron in the high-dimensional space survives under mapping by A to become a K minus 1 face of the low-dimensional. So let's think about that for a minute. So here, you see those vertices? There's 4 vertices visible to you in this low-dimensional projection, but the octahedron has some other vertices that did not survive. If you happen to have, as the underlying image, something that corresponds to one of those vertices, namely, it has a 1 in one position and zeros in all the others. For certain of those positions, it survives, and for others of those positions, it doesn't survive. So in some cases, the L1 norm is going to give you exactly the same result as L0. In some other cases, it doesn't. And so if you understood this, then you'll say, well, things are looking really bad for the home team. Because it seems that, based on my low-dimensional intuition, we have no hope. I cannot think of a way to take an octahedron, rotate it around, look at it from any angle where I don't see some things getting lost in the projection from, say, 3 space to 2 space. And actually there isn't. Like, it's a theorem. If you look at Branko Grunbaum's book on convex polytopes, you can't project, like, from 3 to 2, something's going to get lost. And if you try to do it from 4 to 3, something's going to get lost. So it seems like this can't work. But it turns out, if you go to high dimensions, miracles all over the place. You don't lose. So, for example, here you have a way to do an asymptotic analysis. Let's imagine that A is a random matrix, Gaussian, and you have, so you can think of it as coin tossing, but that's not really the calculation that we do. And we have an index controlling sparsity, an index controlling undersampling, index controlling problem size. We get really big problems, and we allow the sparsity to approach a limit of a certain average density. We allow the aspect ratio, the shortness and fatness of our matrix, to approach a limit. And then we're going to do all the calculations about what happens in lowering the dimension on the convex polytope Cn from capital N space to little n space. And what happens there is the following phenomenon, is that there's a certain regime in this delta rho diagram that we can make where we always get correct recovery in the high dimensional situation, and there's another regime where we never get correct recovery. And we can see that in this diagram. So this is from a paper with Jared Tanner, who was a postdoc for me at the time, is now a professor at Oxford. So on this axis, we have the undersampling fraction. So 1 is no undersampling, and this is extreme undersampling, where we have an extremely fat and short matrix. Here's the density in the vector that we're talking about, what fraction of non-zeros. Black is an analytic prediction from a calculation that we make. And here are results that we got empirically. Namely, what we actually do is construct lots of these cases and see when is the L1 solution exactly the same as the L0 solution. It happens that above this curve, we predict asymptotically it doesn't happen. But at n equals 400, what happens is above that red curve, at least 90% of the time it doesn't happen. Below the blue curve, at least 90% of the time it does happen that L1 is equal to 0. And the width of this curve shrinks down as n gets large. So in the large system limit, this theoretical prediction right here becomes perfectly where things happen from. If you're down here, the relation between the undersampling that you're doing and the sparsity that you have allows exact recovery. And if you're up here, the relation is that you don't have it. And this is all doing calculations on very high dimensional convex polytopes using ideas out of combinatorial geometry. So there's some papers down here that we wrote where we use some exact methods out of integral geometry that were developed going back into really classical work on integral geometry. Rolf Schneider and Anatoly Vershik were two of the authorities in that area. And we used those exact formulas and developed exactly the solution of what this phase diagram looks like. It turns out that although you can do these calculations in the Gaussian case, that you can do experiments all over the place. You don't have to have Gaussian matrices. You can do coin tossing. You can do partial Fourier and so on and so forth. We did massive experiments taking numerous CPU years to do. And if you consider the prediction that we made in the previous plot, then what we found is the empirical evidence for any matrix ensemble that we picked was lying right along there, of course with little fluctuations. The upper curve is something we could discuss later. Later we learned that you didn't even need random matrices. You could take various fixed matrices and simply randomize the position of the non-zeros in your sparse vector. With a class that I teach at Stanford, the first lecture in the class was today, but I'm away. We published a paper in PNAS earlier this year based on all the students crowdsourcing the research among everybody in the class. And we were able to discover that if you take all of these well-known short but fat matrices out of frame theory and combinatorial design theory, what we were able to find is that in every case we could come up with an experiment like this. The Gaussian theory that we calculated previously was here, and what you found with these purely deterministic matrices but random positions of the non-zeros, spot on. And in this particular case, this is a very easy matrix to define, and you can check that one if you want. We later found that not only L1 does this, but there's a number of other algorithms like stepwise regression that statisticians do. Here's a cover of the Phil Trans. That's a diagram of work of Vicky Stodden's thesis that found the exact same pattern happening. And then Jeff Blanchard and Jared Tanner did work with a greedy hard thresholding algorithm at truly massive sizes with many GPU years and got all these data points that lie right along the curve of the Gaussian result. These exact results are different than what people were doing in the very early days. So if you look at the original Condez-Tau results, or their strengthening later by Foucault and Lai, or what people in geometric functional analysis were doing, they were coming out of the culture of we just want inequalities. And the kind of results that we're getting with polytopes is we want actually the result. And you've got to show us what it's going to be. So what's the takeaway message for now is that if we have a random underdetermined system and there's a sufficiently sparse solution, then we can do L1 minimization and find it. We can say exactly what sufficiently sparse is because there's a precise trade-off which can be settled by calculating these phase transitions in the properties of the face lattices of random polytopes. Moreover, these seem to be universal in some sense. And by the way, Andrea Montanari from EE at Stanford and co-authors have recently published a paper proving a kind of universality here. Well, we've talked about exact recovery now, and scientists would say, well, exact recovery is assuming no noise, but that's completely a specious line of research because any real data has noise. So don't tell me what's going on just when there's a perfect observation. Tell me what's going on when there's noise. Or you could say, well, I don't like the idea that I have to be exactly k-sparse. I want to just say I'm approximately k-sparse and then see if I still get a result. So, there's a way to formalize that, and you can allow Gaussian noise in the measurements, normalize it in some sense, and define what we'll call the noise sensitivity, where you take the mean squared error as a function of the noise level and divide by the noise level. This is sort of a coefficient that says how sensitive you are to adding noise. And you can see how that goes. And when you do that, it turns out that the same phase diagram as before, there's a forbidden zone where you wouldn't have been able to do anything even with no noise. And now in the zone where previously you were exact with no noise, here is how the log of the sensitivity coefficient goes. Obviously, it blows up as you approach the edge, and you can do the calculation now using the methods that we published. You can also explain exactly what's the optimal way to cope with the noise by mixing together the L1 and L2 norms, and this is what the appropriate mixture is. That would be using an approach like this, which in Scott Chen's Stanford thesis we called basis pursuit. Today it's often called lasso, after work of Rob Tibshirani on something of this form. Relaxing strict sparsity, we could consider the problem of if you give me an object that instead of being exactly k-sparse is just approximately k-sparse, can I get an inequality that says my deviation from the thing that's truly the solution to the equations is just some fixed multiple of the best k-term approximation. So in the early days of these things, Condez and Tau, Piotr Indyk, and others developed that you could have inequalities of this form. Our goal has been to get the precise constants and exactly the precise domain of validity of these kinds of things as a function of the undersampling and sparsity. The first results of these kind were gotten by the team at Caltech, Babak Hasibi and his grad student, Wei-Yu Zhu, who took our earlier work with Jared in combinatorial geometry and kind of added an extra variable. With Galen Reeves, we worked out a different approach to this that handles many more cases than just p equals q equals 1, so we can sort of do all p and q. And what you get there is something of this form. There's the forbidden zone that we had before, and then there's the good zone, and then you can see exactly what the coefficient of how things blow up as you relax sparsity. So you're pretty tolerant to deviation from sparsity here, but as you approach this critical sampling, you're very intolerant, and you really need sparsity to be quite strict. And you can do it with various p and q. There are other regular polytopes. Those correspond to other optimization problems. Positivity constraints corresponds to the simplex. Box constraints correspond to hypercube. They have phase diagrams associated with that. Jared and I worked out the situation for that. Another thing you could do is play with the scalar field. For example, have complex scalars. And Ariane Malecki, my graduate student, and his co-authors worked on that problem. And Andrea Montanari and Ian Johnson and I worked on a framework that included that problem. So this is what we saw before in the case of the octahedron L1 norm. But if we know that we have positive coefficients, we would be here. If we know we have complex coefficients, we would be here. And if we just know we have bounded, we would be here. So there's completely different setting going on in each case, and the arguments are different, but there's sort of a general framework. On and on. There are many other of these diagrams that we could work out, and more specifically, other optimizations that we could consider. We could consider, for example, sparsity of a different kind, where we have an increasing function where the jumps are sparse, or we have a function whose derivative changes rarely. And these things can be worked out. You have an analytic formula for where the phase transition is, and in rather small experiments, you already see that it's spot on. More recently, there have been interest in problems to do with going beyond the sparsity case to a whole new collection of problems. In these problems, we imagine that we're trying to recover a matrix rather than a vector. We have measurements of the kind that we've been talking about after we turn the matrix into a tall vector. And we ask, can we recover the original array of numbers from the measurements we make when we want the array to correspond to a simple array? One way of defining it is the analog of an L1 norm for matrices called nuclear norm. And what replaces sparsity in this setting is having low rank, or more specifically, the rank of the matrix X0 is much smaller than the minimum of the number of rows and columns. Mariam Fazel's Stanford thesis in 2002 started this type of question, and then all sorts of very significant results were gotten in the last few years on this. We're now at the situation where we have a general framework that derived the phase diagrams in all the previous cases we mentioned, and in this one using one calculational technique. We can consider matrices we know to be just general matrices or non-negative semi-definite. We can have a prediction and observe exactly that algorithms in rather small problems actually fall on the line. Recently, Hasibi and co-worker, and Amelungsen, Trop, and others actually have proofs of these kinds of results. So we've made a lot of progress in how to deal with simple objects, not merely sparse objects. We can generalize sparsity in some way to consider objects with more complex properties, but where there's still some underlying simplicity like low rank. There's a number of things that we could talk about at this point, and I know that President Chen wanted me to talk about the single pixel camera. I have some slides on that Rich Baranyuk at Rice, who's the developer of that, has sent me. We could talk about compressed genotyping, which is screening for rare diseases using next generation sequencing like Illumina machines. We could talk about high resolution radar, or we could talk about work in quantum state tomography. All of these things are possible continuations at this point, but I thought I might have a more important message to say here with the few minutes. I think I have a few minutes left. Tony, if I may, I'd rather bring in another message just at this point. And what that is about is, what is the role of math in this setting? Why did we have to have math going on? What role did mathematical understanding play? So I need to tell you the prehistory of all the math and the failure that was implicit in all that prehistory when we didn't have the math, so that you can understand what the contribution of math can be. People have dreamed of undersampling for a long time because, after all, if you don't have to fully sample, you're saving effort. Why wouldn't you want to do that? So if you go back in the late 1970s, already people had noticed that minimum L1 reconstruction in certain problems gave you sparse results. They had noticed that seismic signals often were sparse, and there was a suggestion that this should be something to be exploited, happening through several papers. In astronomy, where you have astronomical images, of course, they're nearly black. There's black all over the place, and then there's some white spots that correspond to the galaxies or the stars that you're looking at. And people wanted to use some sort of sparse processing. There was a method called CLEAN that was developed in the early 80s. In NMR spectroscopy, Richard Ernst, who got the Nobel Prize in NMR spectroscopy, he spent a considerable amount of time in the mid-1980s trying to do better than just the basic NMR spectroscopy experiment. And he actually wrote papers suggesting we ought to be able to use the sparsity of spectra in some way. He tried to do it in a preliminary way. Jeff Hoke, who has been a co-author of mine in the early 90s, already, as I'll show in a minute, started to work on doing undersampling. You started to see in MRI and in SAR discussion of undersampling in the late 1990s, and then you started to also see various papers, for example, information theory and sparse and signal processing on these topics. And so let's go through a couple of these. So here's some papers by Jeff Hoke. So Jeff and I were at Harvard as graduate students together. I was a graduate student in statistics and working with Peter Huber, and he had a deal with Martin Karplus in the chemistry labs to share a computer. Jeff was a physical chemist, and we spent lots of long nights in the freezing room of that computer that was like super air-conditioned, sort of like Hong Kong. But anyway, it gave us very warm feelings towards each other, and we've interacted over the years, written papers together and so on. Jeff wrote several papers in the 1990s where all the basic ingredients of compressed sensing are implicitly there in the abstract. And it's not really implicit, it's sort of everything that, what are the ingredients that you need? Nonlinear reconstruction, undersampling, et cetera, et cetera. He's not using L1, he's using maximum entropy, but quite similar ideas, and definitely undersampling, and definitely he's onto it. He gave examples showing that he could, instead of undersampling in a systematic way, he could undersample randomly, and he could get a very nice spectral reconstruction through random undersampling, whereas ordinary undersampling would give all sorts of artifacts. Yoram Bresler, who's at Illinois, Michael Gaspar, who's now at EPFL, and a student, they talked about something called image compression on the fly, where they said you ought to be able to undersample. They had a diagram in this one-page abstract in the late 90s. I guess people were afraid of using too much paper. They didn't explain how you decode it. So they just clearly wanted to undersample. They left this kind of vague. Martin Vetterli talked about the idea that if you have what he calls finite rate of innovation or sparsity, you ought to be able to get by with fewer samples. And actually, by this time, in this thesis, which was submitted in June 2001 by Frank Vagier, he has in this thesis a lot of things. Undersampling in the Fourier domain, he's doing MRI with the undersampling. He's exploiting a kind of optimization that's, however, non-convex, but by gradient methods, he's getting some kind of quasi-solution, and he's getting good results. It had no effect. In fact, all the things we're showing here really didn't have the effect that we think they should have had in retrospect. What you need for compressed sensing is three things. You have to have sparsifying transformations. Like you can sparsify your class of images with a known transform. You have to undersample in a kind of random way. And you have to nonlinearly reconstruct, for example, with the L1 norm. If you don't have those three, you haven't gotten it. Each of the authors above sort of knew that you had these three things. And Jeff Hoch sort of said you had to have those three things. So why didn't this catch on? Why have we only started to see things starting in 2004? Well, here's the deal. There's a massive amount of research out in the world that's basically computational now. You have the computer, you can go and ask questions of the computer, you can publish the results, you can show things. That's exactly what those authors were doing. Jeff Hoch was showing real experiments on the computer that were showing that you could do things. Even as far back as Dick Ernst, they were doing the experiments physically, then they were doing the reconstructions on the computer, then they were talking about it. No one paid any attention. It was like this massive effort to do computational science and nobody believes it. Why is that? Why don't we believe other people's computational results? Well, it's not reproducible. It's just a kind of advertising where you're just telling people you did something. And, why is anybody going to believe that? Now, we should do more. We should be reproducible because there are regulations that say you're supposed to give your code away and you're supposed to give your data away. Very few people ever do it, and there's no enforcement of this. What happens if researchers don't believe each other's results? Progress is not cumulative. You can't build on what other people do. The risk to you in a non-cumulative field is that you see something great like compressed sensing and everybody ignores it until someone else comes along and they start paying attention to that other person. And why would they pay attention to it? Because they believe it. And why would they believe it? Because it's not computational, because it's actually math. And if you follow the kinds of computational publication practices that people now follow, you're just going to be reinventing stuff that gets ignored again and again and again. At least people believe that if it's been proven mathematically, it really is reproducible. They will believe that. Okay, so John Claerbout, who also worked in the L1 at the beginning, pointed out that there's a crisis. He says, computational science in scientific publication is not really scholarship. It's just advertising. The actual scholarship is everything you did, the full software environment. If you're not giving it away, it's just advertising. So we've tried over the years to publish everything that we do. I won't say we're perfect. I won't say that it always works. My postdocs often disobey. My graduate students rarely disobey. Funny how that works. There's a movement towards reproducible research in computational science, and perhaps it will work. Perhaps. There are special issues that have appeared in IEEE Computers in Science and Engineering. There's articles on reproducible research and signal processing. There's resources at reproducibleresearch.net. Victoria Stodden, who was my student, is one of the prime organizers in the reproducible research movement, and she also tries to get major media to pick up stories that she writes on this crisis. So there is, a very substantial effort, but it's sort of 1,000 people misbehaving to everyone who cares. But just remember, if you're one of the misbehavings, you're working in a non-cumulative field. You're spending your whole life doing stuff that might as well be ignorable by other people. Why would you do that? Why don't you change your field so that you have cumulative knowledge and you can believe that there will be some lasting impact of what you do? The way to do that is to learn to work reproducibly in your computations. Otherwise, some mathematicians are going to come along and steal your thunder. Okay, so this is a rapidly developing area, lots and lots of papers since 2004. Many heuristic efforts before 2004. There was a logjam until 2004 that I think was created by the mistrust of computational results. Theory broke the logjam because people realized that the stuff that they'd been hearing again and again actually was true. Oh my God. And then suddenly, practitioners really started making a lot of progress. They gave themselves permission to work on this, whereas before they disbelieved it. Let me give a few moments here for credit in various ways. I'd like to thank collaborators that I've had in the story. This is not everyone that I've worked with. It's just the ones that are related to our story directly in some way. So my most frequent co-author has been Ian Johnstone, who's a professor at Stanford. Phil Stark and I started work on Sparsity together when we were much younger. He still looks pretty young. Tex Logan, fantastic fiddler and really one of the great harmonic analysts of the second half of the 20th century. A privilege to work with him. Jeff Hoke, who discovered a lot of stuff very early and was unjustly excluded from credit. Scott Chen, we worked on L1 minimization in the early days. Manuel Condez, we worked on sparsity in other ways. He went away, left the nest, and suddenly got interested in this L1 and came back. Xiaoming Huo, we developed the theory of L1, L0 equivalence together. Yoav Benjamini worked with me starting on sabbatical in Tel Aviv years ago. Mickey Alad, Jean-Luc Stark, Jared Tanner, Michael Lustig, the golden 4 postdocs you could ever have. These guys have, between them, what they've achieved is just completely awesome. Graduate students that I've had, Jashun Jin, who people at HKUST know, Victoria I've mentioned, Yaki Tsaig, and Ariane Malecki were some recent students who both worked on things in the compressed sensing era. Andrea Montanari is faculty in EE, definitely a leader worldwide in information theory these days. Galen is a just finished postdoc with me, and here are my current graduate students. Each of them I've had papers in PNAS this year. I'd like to thank all my collaborators over the years, and you can see that a big part of success is being kind of part of a movement. All of these people put their youthful energy into this cause and really made it get somewhere, and I'm just like a part of it. I'd like to point to a couple of things. No one has mentioned the fact that the Shaw Prize is about money, and I just thought I would mention a couple of things. So my wife and I decided to redistribute the funds to various charities and universities. And so first of all, I'll just mention Lingzi Liu was a master's student at Boston University. Maybe you can read this. She was killed in the Boston Marathon bombing earlier this year. And there's a joint effort of the American Statistical Association and the International Chinese Statistics Association to create a memorial in her honor that will allow a practical statistician, which is what Lingzi was preparing for as a master's student, to attend a special meeting of the ASA in practice. So one thing that Mickey and I were able to do is match all the existing contributions to that, and it put that fund over a limit to endow it securely. In particular, I would like to thank a former PhD student of mine, Eric Kolachik, is the chairman of the math department at Boston University, and he's the person who organized this fund in her memory. And it's really a horrible tragedy. I've taught master's students for a number of years at Stanford, and we do get many students from abroad, from Korea, from China, and I've seen in the past from many other countries. And they're all trying to learn, statistical practice. I've taught master's courses. I usually teach 1 or 2 of these a year. So it really meant something to me, and then on top of it, it was my own former PhD student who was trying to organize this effort. So I'd like to thank the Shaw Foundation for helping actually what's a grassroots effort from the statistics community to try to do something to make good out of this horrible tragedy that happened earlier this year in Boston. Another thing that I'll just mention just quickly, can I make this big enough? Probably not. There's a Museum of Mathematics in New York that just opened December of last year on 12/12/12. And another thing that Mickey and I have been able to do with the Shaw money is to make a substantial donation to the Museum of Math. The idea of this is to, it's a very interactive place. It's in an important global capital. There are not really many math museums, and the ones that exist tend to be kind of around more at the scholarly level. But this is more getting kids involved in math. It's an interesting initiative. Finally, most of the money has not gone to these causes. It's gone to research. Michael Lustig was my co-student with John Pauly at Stanford. He's now a junior faculty at Berkeley, and we gave funds to him in order to support his research towards making his methods reproducible, because he's doing wonderful computational work, and I would like all the code and data to be published so other people can spread that out. Also, money has gone to Stony Brook University for an educational project there, and money will go to Stanford, where it will support either reproducibility of the effort that you saw in pediatrics, or work by Ian Johnstone and myself as we supervise students. Graduate student support at Stanford is about $61,000 a year, so this would be able to support a number of graduate students over time. Anyway, that's where the Shaw money is going, in case you were curious about it. Thanks again.
So we have some time for questions. Yeah, so if you have a question, please raise your hand and send a microphone to you. Okay. Over there.
Thank you, Professor Donoghue, for your contributions to charity. That's really, really great of you. I wonder if there's any truth in the rumour that your best ideas for coherent recovery come from your own recovery after ballroom dancing.
Well, okay, what has ballroom dancing done for me? And what has it taken from me? What it has done is it's put me in the constant supervision of very strict academic judges but judge on totally different criteria. One thing, for many years, they challenged me to smile. They challenged me to not look at my feet. I didn't understand how badly mathematicians are postured and how poorly they relate to other people until I took ballroom dancing lessons. The old joke about mathematicians is the only difference between a pure mathematician and an applied mathematician is that the applied mathematician looks at your shoelaces while he's talking to you, and the pure mathematician looks at his own. Okay, so by taking ballroom dancing lessons, I was encouraged to look up, I was encouraged to smile, so on and so forth. Now, there is a cost. There's a real cost to it in time, and also I feel that these postural habits of mathematicians are kind of important. I think that we look down because we don't want to engage with other people. We want to continue in the stream of thought that we have. And so it's an extremely helpful way to avoid seeing other people and interacting with them. And so then when you get taught to interact with someone, it's kind of defeating a lot of what you want in life, which is to get away from people. But I've learned to interact with people from that, and so that's been good. What I hope is that the time invested will give me some kind of generalized benefits that will give me a longer, productive life. I still get things where I'm in some dance lesson and I just want to go write something down.
Can we do complex sensing in an adaptive way? I mean, as we collect more data, we understand better the sparsity property, so we get to know really how many samples we need. So we can save, maybe.
Right, so okay, so in this talk, I mean, a very broad audience, including secondary students, so there were some things we didn't get to. One thing that we didn't get to was, can you push the phase diagram like all the way? What's the best phase diagram you could get? What we started here was, what's the phase diagram of L1? Or what's the phase diagram of nuclear norm minimization? So, once you learn how to calculate that, then you start saying, well, could there be some algorithm that's even better, et cetera, et cetera. Okay, so there's an idea coming out of statistical physics. There's notions, it's called spatial coupling in the information theory literature, but it comes out of some crystal nucleation idea in statistical physics. And it's not what you suggested in the sense that it's not actually adaptive, but it's a very complex staged procedure, but there's no feedback. You start at the beginning and you do something extremely specific in the kind of measurements that you make, and then you get more and more measurements of a very particular kind that I could sketch at the board. The key thing is the algorithm to post-process is very highly adaptive. The measurements are still fixed and they're very special. Instead of being a random matrix that's completely dense, it's got randomness elements, it's not dense, and you're trying to simulate a process that's understood. If you take, you can take water that's very pure and you can freeze it, or you can, get it colder than freezing and it'll still stay liquid. And then you can, drop a crystal of ice in it and then all of a sudden the whole thing freezes. And that idea coming out of physics with implementation through statistical physics has been developed as an algorithm for compressed sensing. So there's some really great stuff. Look, I mean, if you got thousands of papers in something, you know that there's a lot of stuff there that we could talk about. Yeah, so that work, by the way, so it's a paper of Florent Kurzakala and Marc Mézard, if you want to follow up on that. And the keyword is spatial coupling. And there's follow-up. There's a paper on arXiv by Andrea Montanari, Adele Javanmard, and myself.
I completely agree with you on the reproducible work. I noticed that your first plot is made using R software, and following that, you using MATLAB. And in the end, several plots, you using R. R is a free software. So MATLAB is very powerful, but it's not free. So I was very surprised that you are learning use. I noticed that actually on your laptop, you have both MATLAB and R. It's quite interesting
Oh, really?
comment. You have both software, R and MATLAB. It's a
Yeah, I don't, okay. I don't think that this is an economic issue, although it may be to you, okay? But even among, so reproducibility to me means that you work in a way that you plan to reproduce it. So you plan that all the code that you may do is going to be published from the beginning, and right? Now, to me, imagine there was an access charge for the paper of $29 or whatever Elsevier is paying. But for that $29, you got all the code. I'm okay with that. I mean, I don't care about the aspect of the money. I care about the fact that it allows science to be cumulative. So I just want to make that point different. I agree that R is a great effort, but I also agree that MATLAB is a great thing. So I don't want to, discriminate one against the other, and I'm very happy to have both on the computer. I'm not going to get rid of either of them.
Thanks, Professor Donahoe's talk. I'm working on the applications of compressive sensing and noticed that a recent paper report that the non-convex relaxation often produce better results than the L1 norm in real applications. So I just wonder, is there any theoretical justification for using the non-convex relaxation? Or if the non-convex relaxation can relax the conditions for the exact recovery? Thanks.
So I'm not sure about the paper you're referring to. So it's not, I'm not exactly sure what to say.
Using a non-convex relaxation to replace the L1 norm, the convex relaxation, to get the better results in real applications.
Okay, so you're saying there are some other combinatorial optimization problems besides the L's. So L1 is the convex relaxation of L0, right? So we can
Yeah.
agree on that. Are you talking about maybe there's another combinatorial optimization problem and the convex relaxation of that is not very good?
They do it. They use a non-convex relaxation. For example, they use a L0.5 norm. This is just an example. They show the results in real applications. Some applications, for example, in computer vision, they can get better results than using an L1 norm.
Oh, non-convex, you're
Yes.
saying. I'm sorry, I thought you said convex. Okay, so the problem with non-convex is that because it's non-convex, there's no theory. There's no theory showing that you can actually do it, right? So you can write all sorts of interesting papers. Hypothetically, if you could solve this non-convex optimization problem, it would be great, right? I mean, but
So just
I don't know how scientific that really is. To make a hypothesis about an impossibility, it's a little too utopian. But I can agree that it would be great if you could solve non-convex. I mean, sure, you just can't imagine what would happen. We could crack every code and hack every computer overnight and tear the world economy apart. I'm just unbelievable what we could do.
Okay, I think we need to wrap up because there's a lecture soon. So let's thank Professor Donahoe for a fascinating talk.